So next we're going to look at an example where we want to find this triple integral, and our region is given by a tetrahedron with vertices 0, 0, 0, 2, 0, 0, 0, 2, 0, and 0, 0, 4. Notice that our function on the interior here, the function that we're integrating over, our density function, is just a function of x and y. It could have a z variable if we wanted. So first let's sketch what this region looks like, because the hard part is setting up our bounds of integration. We say that the tetrahedron has a vertice here, a vertice at where x equals 2, one where y is equal to 2, and then one where z is up here at 4. So we're trying to find the bounds for this shape. The way that we go about finding the bounds for 3 dimensions are, first we want to find what are the bounds on the base, and then we need to find the bounds on the height. So for step 1, we need to look at the bounds for the base. And typically I like to think of the base as the base in the xy plane, because that's what we think of as the bottom of the function. But I'll step through a second example where we think of a base as being one of these side walls. So for the bounds on the base, I'm looking down at the xy plane. So this is my top view, and we see that our points of intersection are where x equals 2 and y equals 2, and it's this triangular region. So if I look down on this tetrahedron in the xy plane, I would be left with this triangle down here. And so step 1 is actually pretty easy. It's a review from what we just did, that I want to find the bounds for this region, and I can think of it as either a type 1 or a type 2 region. And in this case, I'm going to think of it as a type 1 region with these horizontal segments. Oh, and this is similar to a section we did before. My x values are going from 0 to 2. Those are boring. And my y values are going from y equals 0, this line down here, up until y hits this line up here, and this line has the equation y equals negative x plus 2, right? Because it's a line with slope -1 and a y-intercept of 2. So that means my y's are going from negative x plus 2. You could write that as 2 minus x. So now we found the bounds for the base. And next, step 2, we want to find the bounds for the height. I need a new piece of paper. Step 2, bounds for height. And this is a little bit trickier given the setup of this problem, that we need to know what is the z value, the z coordinate at each of these heights. I'm sort of thinking of, because when I'm down over here, my height is really little. When I'm over here, my height might go up to here, and right at 0, 0, the height is all the way up at here. And what is an equation for all of these heights values? Well, it's the equation for this plane. In this case, it's the plane that intersects where z equals 4, where x equals 2, and where y equals 2. So I need to come up with an equation for this plane. We know that planes have, this is my cheater method, quick method. I know that planes have an equation ax plus by plus cz equals d, right? And one way to go about finding what all of these values would be is to find a normal vector to this plane, and then use the fact that one of these points is a point on the plane, and use the point normal vector form to be able to come up with the equation of the plane. I'm lazy, and so because I have the information about these intercepts, I'm going to use a quick method. And my quick method is to just read off each of these coefficients based on the fact that I know what the intercepts are. I'm given information about this plane that makes it easy. I'm going to set my d equal to 4, And I'm doing that because 4 is the least common multiple of all of the intercepts. And you'll see why that makes sense in a second. 4 is the least common multiple of 2, 2, and 4. And when I set d equal to 4, so I'm going to set my lowercase d equal to 4, I can just read off if x is 0 and y is 0, I would need my c coefficient to be what in order for plugging in 4 for z to give me a d value of 4. Essentially what I'm saying is 0 plus 0 plus c times, when x and y are 0, it gives me a height of 4 equals 4. That means that c has to be equal to 1. Similarly, so here I'm plugging in the point 0, 0, 4. If I were to plug in the point 0, 2, 0, that would mean 0 plus b times, oops, you can't see this, sorry. 0 plus b times 2 plus 0 has to be equal to 4. And this is because the point 0, 0, 2 is the point right here, where my y is equal to 2. And that means that my b value has to be equal to 2. And finally, I can plug in my x-intercept, which is 2, 0, 0. So I get 2 times, whoops, well, where x is equal to 2, my coefficient I called a times 2 plus 0 has to be equal to 4. And that means that a is equal to 2. What does that mean? The equation of my plane is going to be 2x plus 2y plus 1 times z, or z, is equal to 4. Notice that I didn't need to let my d equal 4. It was convenient for the arithmetic in this case. If I let my d value equal 100, I could have done the exact same work, and it would just mean that my coefficients were different. Why did I do all of this? This is just to give me the equation of my plane. Why is the equation of the plane helpful? It's because it tells me my heights. In my tetrahedron, going back to my picture, in the tetrahedron, my z values go from 0 up until I hit this plane. So I solve this equation in terms of z, and I find that z is equal to 4 minus 2x minus 2y. And so my bounds on z are going to be from 0 until 4 minus 2x minus 2y. And that gives me all of the bounds that I need to set up this triple integral. We found in the previous, our previous work gave us bounds on x and bounds on y, and now we have our bounds on z. And so when I set up the triple integral, I know that my integration should have constants on the outside, so my x values are on the outside, x equals 0 to 2. Now, this is the next tricky part that we haven't talked about because we have multiple variables, but it makes sense that as I work outside to inside, I can get more and more variables as I go in, meaning that my bounds on y only have x's as variables, whereas my bounds on z's have both x's and y's. That means that these bounds must be the most inside. So my y values in this case go from 0 to 2 minus x, and my z values go from 0 to 4 minus 2x minus 2y. And remember, we were integrating over the function x plus y. So my triple integral is x plus y dz dy dx. And now I can compute this integral doing triple integration. I'm not going to compute it just yet. Instead, we're going to interchange the order of integration. Let's review what we did first. So first, we found a picture of what our region looked like. Then, given this picture, we found the bounds for the base, using a type 1 region in this case. Next, we found an equation for the height. And in this case, the equation was a plane, and those gave us the bounds on our z value. Let's see if we were to do this in a different order. So I'm going to interchange the order of integration. So by interchanging the order of integration, I'm no longer going to think of this base being in the xy plane. Suppose I decided to think of the base as in the xz plane. There are reasons why we might want to do this based upon what we were actually having to integrate over. For us right now, it's actually more of an exercise. So in this case, my step 1, I want to find the base, and I'm thinking of the base in the xz plane. So let's look at what this looks like in our 2 variable space. Our x value has an intercept at 2, whereas our z value has an intercept up here at 4. And it's this straight line and the triangle section. So what are the bounds on this? I can think of my x's going from 0 to 2 still. But my z values in this case are going from 0 up until this line. What is the name of this line? The line has a slope of -2, so z is equal to -2x plus 4. Let me check and make sure that that's correct. When x equals 0, we're up here at z equals 4. When x equals 2, we're down here at z equals 0. Yeah, that's the correct equation for that line. And so our z values in this case are going from 0 up until this line, which is the line given by, I'll rewrite it as 4 minus 2x. And now we have the bounds for the base. And our step 2, we need to think of our bounds. Step 2, bounds on the height. Height is a weird word to use here because we're sort of visualizing turning our tetrahedron on its side, right? Because our base is over here in the xz plane, and it means that our heights are instead extending out sort of in the y direction, right? But our steps are similar to what we did previously, that we need to have this equation of the plane, but this time the equation of the plane should be written in terms of y. So when I look at the bounds on the height, I need to know the equation of the plane in terms of y. And we already found the equation of the plane previously, and it's still the same plane, so there's no extra work that we have to do there. The equation of this plane, recall, was given by 2x plus 2y plus z equals 4. And so when I solve for y in this case, my y is equal to 4 divided by 2 is 2 minus 1/2 z minus x. So our lower bound on y is 0, just because of the tetrahedron starts where y equals 0 and it extends out to this plane. So the bounds on y go from 0 to 2 minus z over 2 minus x. And that means that our triple integral, sorry, you can't read over that, z over 2. Our triple integral, the order of integration has changed. The constants on the outside are given by x, so x is going from 0 to 2. The bounds with the next fewer number of variables is this one, so my z coordinates are going from 0 to 4 minus 2x, and my y values are going from 0 to 2 minus z over 2 minus x. And notice that we don't do anything with our density function. It's going to be the same no matter how we rotate our three-dimensional object, dy, dz, dx. And if we wanted to, we could interchange these in whatever order we wanted, but you would have to make sure that you would reconceptualize what the base of the region looks like and what the height of the region looks like in order to have the proper order of terms. I'm all done with this example, and I will go on to the next example in the next video, but for those of you who want to see the practice of actually integrating this, the rest of the video will be integrating, computing this integral. And yeah. So recall the integral is given by the integral from x equals 0 to 2, z equals 0 to 4 minus 2x, and y equals 0 to 2 minus z over 2 minus x. And our function is x plus y dy dz dx. So our first step is to integrate with respect to y. So our inner part becomes xy, treating x as a constant, plus 1/2 y squared. Oh gosh, this is a messier. I should have done it from the other one because this one is actually going to be pretty messy. Oh, sorry, you couldn't read any of that. We still have our double integrals on the outside, dz dx. And I'm plugging in my bounds from where y equals 0 to y equals 2 minus z over 2 minus x. So that means I have x times 2 minus z over 2 minus x plus 1/2 of 2 minus z over 2 minus x all squared minus plugging in 0 for y gives me 0. Again, I still have my double integral dz dx. I'm going to do a little scratch work to the side because I want to have to square this, and I don't want to have to do that in my head because I might make a mistake. I might make a mistake anyway. So when I squared this, this is just scratch work. And I also have to multiply it by 1/2. So I square it and I get 4, and then I get a minus z and then another minus z, so that means minus 2z. And then my next terms, I get minus 2x, and another minus 2x is minus 4x. That's multiplying my 2's by everything. Next, I get a positive z squared over 4, right? And then a positive xz over 2, and another positive xz over 2. So that just becomes a positive xz as I add them together. And then finally I have my x squared term plus x squared. Let's check and make sure that that's correct. I have these terms, I have this and this and this and this. I have that squared term, I have that mixed term. Yep, that should be it. And now I multiply all this by 1/2, and I get 2 minus z minus 2x plus z squared over 8 plus xz over 2 plus x squared over 2. Great. So that's my scratch work for this piece, and that's just algebra. This is something that your 10th grade algebra student could do for you if you had hired labor to be able to help with things. So continuing on, I'm multiplying the x by this term, and then I have to add all of this stuff. So I plus 2 minus z minus 2x plus z squared over 8 plus xz over 2 plus x squared over 2 dz dx. Combining terms, I have a plus 2x and a minus 2x. I have a minus xz over 2 and a plus xz over 2. I have a minus x squared and a plus 1/2, so that'll be a minus 3x squared over 2. And then plus 2 minus z plus z squared over 8. Phew! dz dx. So now I integrate with respect to z, and I treat this and this as a constant. So I end up with negative 3x squared z over 2, that's just a constant, plus 2z minus 1/2 z squared plus 8 times 3 is 24z cubed, and I evaluate that from where z equals 0 to 4 minus 2x dx. So when I plug in z equals 0, all these things go to 0, so I only need to plug in and worry about where z equals 4 minus 2x, and I get negative 3x squared times 4 minus 2x all over 2, plus, I can do this in my head, 2 times z is going to be 8. Oh, sorry. 2 times z is going to be 8 minus 4z. No, 4x, because I'm plugging in this. And then minus 1/2 of z squared. This squared is going to be 16 minus 4x plus 4x squared. Plus, this term cubed is going to be the squared term times this term. Let's see if I can do this in my head. It's 1/24 of, uh-oh, I'm running out of space. 16 times 4 is big. 128, right? 16 times 4 is the same thing as dividing this by 2. No, it's only 64, because it's 8 times 8. 64, and then minus 16 x's minus another 2 times 16 x's, so I'm subtracting 3 sets of 16 x's, which is 48 x's, and then I have 16x squareds plus 8x squareds. 16 plus 8 is 24, plus 24x squareds, and then I have minus 4 times 2 is 8x cubed. Again, this is just algebra. I'm not really sure why I'm doing all this algebra, but we're almost done. So let's continue. We have 3 times 4 divided by 2 is minus 6x squareds, and then plus, the 2's cancel, 3 x's plus 8 minus 4x minus 8 plus 4x minus, whoops, that's not 4x, plus 2x, 1/2 times 4, and then minus 2x squared plus 64 over 24 minus 48 divided by 24 is 2x. 24 divided by 24 is plus x squared, and minus 8 over 24 is 1/3 x cubed. And now we integrate this as x goes from 0 to 2 dx. And this is just a simple normal integral. And hopefully my work is still valid. I'm sure that you can comment in the YouTube section if I'm making algebra errors. Let's combine some of these. So I have a 3x and a minus 4x, which is a negative x minus another 2x, so that's going to be minus 3x's. I have a minus 6x squared, and then minus 2 more x squareds is minus 8x squared. And then plus an x squared is a minus 7x squared. Ooh, I don't know if that's right. A plus 8, a minus 8. 64 over 24 is, I can divide both by 8, and I get 8/3. Oh, no wonder. So that's plus 8/3. There's an error here. So plus 3x minus 4x is minus 1x. And then these two, the plus 2 and the minus 2 cancel, so this should just be a negative x here. Squareds, x's, great, I took care of that term, and then minus 1/3 x cubed. I'm integrating as x goes from 0 to 2 dx. So that becomes negative 1/2 x squared minus 7/3 x cubed plus 8/3 x minus 1/12 x to the 4th, evaluated from x equals 0 to 2. I plug 2 in everywhere. 2 squared is 4, divided by 2 is -2. Oops. 2 cubed is 8, times 7 is 56/3. 2 becomes 16/3, and 2 to the 4th is 16 minus 16/12. We've gone this far, so I might as well get a common denominator and make it look all nice and neat. 2 times 12 is -24/12. 56 times 4 is going to be 50 times 4 is 200, and 6 times 4 is 24, so I have 224/3. Oh, 12ths, that's why I changed to the common denominator, plus 16 times 4, we've already done this, it's the same thing as 8 times 8, which is 64, minus 16/12. And then we get some number of 12ths. This is 248/12. I have to do side work. 248/12. These are negative. Minus 16, so I'm going to add 16 to that, and I get 14/264. Oh, great. And that's going to be -200/12, which I can simplify. I divide top and bottom by 2, and I get -106, which is equal to -50/3. Woohoo! And we're done.